I'm talking about me. I'm talking about you. Let's get together and have some fun. I don't know how to do it, but it's gotta be done. Star Trek, Journey to Eden. That was just wonderful episode. It was right on the borderline of those, like, it's so bad it's good. It was right there. It was the one, like, Spock is playing the Vulcan harp, and it's like this, like, wild 12-bar blues thing. So, all right, here we got the test bed going again. I just tested it, and it's working. So we're going to gather lots and lots of data, and then we're going to change the coils and gather lots and lots of data. But here, you know what, just to reiterate for people who haven't been following along, you know, you just charge this thing up, and then you discharge it across a coil, and you gather the inductive spike out into this cap, and then later you run it off of this larger cap. And so you look at how much did this cap go down for this cap to go from 0 to 10. And so from that, one can determine the efficiency of your DC-DC conversion. And if you had a situation where this goes from 0 to 10 and this goes from 10 to 9.51, that would be a situation where you have an extremely efficient circuit. If you were to feed some of that back, that would be right at unity. So these are not over unity. So what we're looking at is making a more efficient DC-DC converter. And so, you know, with something like this, when you pulse it about as fast as these can go, I don't know, this will go from 10 to maybe 9.36 or something like that when this goes from 0 to 10. With the 10-pound coil, it's 10 to 9.43 or something like that. But that's a 20-fold increase in your mass of wire. So you want to try to first get an idea of where, you know, the lay of the land in terms of how should the coils be shaped. And so that's what I'm looking at here. And then also, and I think you can kind of see this in terms of the idea of higher voltage and resistance. You know, there's a reason why the high voltage lines are high voltage when they go long distances. And so you can see things begin to behave better at higher voltages. But before you know, I mean, maybe you don't, maybe you know a lot more and are much better. But before I, you know, try to go to like 5,000 volts or something, it's like try to get a bit of understanding of the lay of the land, as I've been saying. And then, as I've also been discussing, when you add a second coil in, there are more variables, and an interesting one is the buck configuration. And so first gather the baseline with this and see how much does this discharge for this to go to 10 volts. And then put two coils in series and repeat it, and then put them in series one on top of each other in just a conventional configuration and in a bucking configuration, and again repeat this. So that's what I'm going to do now, and I'll do that, and I need to go back and take all those 1-second delays out of the code, but I'll go back and do that, and I'll tell you what I saw, the royal we. But we'll all see it together, huh? Okay. Hello, greetings to all, and sorry about the mess here, but just sticking my toe in the water here. I'm starting to gather some data relating to coils and coil shapes and how they behave and things like that. So that this may bore people. It's okay. I actually, one of the things here I find really interesting, and I will I will note that for you. But it's just going to be some numbers. So what I'm doing here is we have, to start off, we have an LCR meter, an induction capacitance resistance meter. And so I'm putting it across the coil, and I'm measuring the induction capacitance and resistance of each coil. The way this thing works is, as I understand it, it has a setting 120 hertz and 1 kilohertz. So I'm thinking it's putting an AC, an alternating current sine wave through at 120 hertz or a kilohertz, and from that it's calculating the inductance and capacitance of the coil. So I've done that for these 3 coils, 1, 2, 3, and I wanted them all the same. They're not quite all the same. We can see the resistance, and even the resistance changes a tiny bit depending on the speed there, so I don't know what's going on with the meter. But my normal voltmeter would just read like 4.8. It doesn't go this accurate. So I don't know if that's just noise or what it's seeing there. But anyways, we can see that the 3 coils have approximately the same resistance. They're close. So it's just about the same length of wire is what I'm getting at. But they don't, these 2 were very close in terms of inductance. 10 millihenries, 10.24 millihenries. This one was less. So either like it was like wound with a bunch of like diagonal, wines going all over the place, or maybe there's a little bit of a short with some of the insulation coming off. But it's not end of the world kind of stuff. It's maybe 10% different. And then capacitance, and the capacitance on this measured meter varies greatly as a function of frequency. So at 120 it's that many UF, at 1 kilohertz it's that many UF. What I've decided is that the measured capacitance doesn't factor into your resonant frequency at all. I mean, it pretty much can't. I mean, I've pulsed this thing at pulses per second at least all over the map, and I've graphed it out, and it's always constant. If this capacitance were factoring in, then you wouldn't have a resonant frequency. You would have a varying resonant frequency because the capacitance that's changing here would factor in. So I'm pretty sure that that can't factor in, but we can see the capacitance of the coil. So this is all well and good. And then what I'm going to do, as I talked about from the last video, is I'm going to make this coil flatter and flatter and flatter and see how those parameters behave. If I have Wheeler's formula for induction correct for single wire air core solenoid, the inductance for this given length of wire, this given resistance, should continue to increase till it's maybe about the size of that piece of tape and out about like that. And then I suspect if you go flatter than that, the inductance will begin to decrease for the given length of wire. Although I need to measure this experimentally for myself. So that's just with the 1 coil. Where's the maximal inductance, as Wheeler was looking at. Recall from the last video and from the definition that inductance, the unit of inductance, the Henry, is defined in terms of the electromotive force. So the more induction you have for a given length of wire, the greater the EMF, because the EMF results from the rate of change of the magnetic flux. And so if your straight line DC resistance is constant, but your inductance is greater, and the inductance is just saying what the EMF is, then that's better. Where things start to become more complicated is if we have 2 coils. And you could I can think of 4 ways that we might arrange them. And the first is simply in series. And I'm not going to bore you with, here I'm measuring it, but I am going to measure that, and that'll be put in series and then in parallel. Now, from the textbooks, what we know is when we put this in series, well, you have twice the length of wire, so the resistance is going to double. And inductors in series, the inductance doubles. And that's what I'm seeing measured on the LCR meter. So that would seem to me like if you're charging a cap or something, that would work the exact same as a single coil, because your inductance is doubled, but your resistance is doubled, so therefore the rate of change of the current, and hence the magnetic field, should be halved. Twice the inductance, half the rate of change, it should be the same. However, when you do the real test of just throwing it into a cap, two coils in series work a bit better than a single coil. And I don't know exactly why that is. I've seen it consistently enough now to say that, yeah, it's there. The second way to arrange these would be in parallel. And there you are going to have the resistance and have the inductance. And I don't think that'll do any better than a single coil, but you'd just be putting more power through because there's half the resistance. Then you can think of putting the two coils on top of each other so their fields are interacting, and in the first arrangement you would have it as one coil, just the current starting here going through up to there and ending. And so that would be a lot like having a coil shaped like this, which would not be an ideal shape, but I want to gather what the various metrics are just to have them in there. And I think it would, I don't know how it would do. I think it might do worse than a single coil like that, just because the thing's too darn tall, and so the amount of inductance for the resistance that you have is not good. Then finally, you could think of this in a bucking arrangement where the current is flowing this way and then down this way simultaneously. That's also a counterwound arrangement. And you can see, and this is what I'll demonstrate for you, you can see some interesting stuff just with an LCR meter when you look at it this way. So let's just look at it in series like this and then counterwound and observe the inductance and the capacitance, how they change. So here I put these two coils in series. I put a little tape on the start end of each of the coils. So we have the start of this coil going out through its end to the start of this coil going through here to the end, and we see that the inductance, this meter is just impossible to read whether it's 100 or, okay, I think this is at 120. The inductance is now 9.49. Let me see. No, this is the resistance. It's a great meter, but they made these things like tiny. The resistance is 9.49. So before we had 4.78, 4.78, 4.9, 4.9. So within the ballpark, yeah, we're at 120. So 4.78, 4.78, 9.49. So yeah, that's fine. And now we'll go to that was the resistance. Now we're looking at the inductance. I think we're still at 120. And the inductance is reading 20.48. So 10.24, 20.22, 20.48. So yeah, it's just about right. Now we'll look at the capacitance just real quick. And it's 60, so the capacitance has halved. So that's all fine and normal, and that's all textbook. Although, as I said, when you're charging a cap, it actually charges a bit quicker like this. But with the inductance having doubled and the resistance having doubled, I don't know exactly why that is, but it is modestly a small amount better. So I won't bore you with the doing it in parallel, but as I said, I'm going to gather that and I'll put the series, put the parallel in. Where it gets interesting is, let's make this towards one coil, and let's see, yeah, and that is arranged in a conventional, I'm sorry, I didn't show you anything. Here, let's do it again. Here they are, and you know, I can flip this coil on its side, I can flip it over, it doesn't care because the two fields aren't interacting. But now I'm going to bring it right on top of the other one. And we've lost, you know, 15% of our inductance. However, our resistance is still the same, still the one length of wire. So that's not good. That's why I'm saying this is not an ideal setup, because now the coil's too tall. But let's put it in a bucking arrangement. Okay, so here we just have it as one coil. Let me see if I can get them both in. I can't, but I can try. And now I will just flip this over like that. Look at that. Now the measured induction is 23.68. So we've got 15% more induction, and of course the resistance is the same. Okay, so per the specs, these things can only switch down to 100 microseconds. I'm actually down to about 60 microseconds. I saw improvement, so they were generous in their specs there. So I have the on time set at 60, and the for loop pulses at 160 times. You know, when that happens, we see that 100 UF cap goes from 0 to 10. And now I'm going to put the meter on the 1000 UF cap. It drifts up. I'm trying to keep it at 10. That's about as close as I'll get. So it's off by 1/1000th. And when the light goes on, we'll see how far this goes down. .32. All right, we have our baseline. So interestingly enough, this 100 UF cap went from 0 to 10, and the 1000 UF cap went from 10 only down to 9.32, when you would expect it would go from 10 down to 9. However, I mean, I'm not going to belabor this, but if you want to feed stuff back, this needs to go to 9.51 and above. Yeah, just to try to, you know, real quick go through the reason for that is, you know, you have this inductive transformation of voltage, and so if it were perfect, you know, when you're going from 0 to 2.5, it would be 4-fold excess. From 0 to 5, 2-fold excess. From 0 to 10, just right at unity, but because of all the excess previously, you would get 2-fold extra, which would put this at 9.5. So 9.51 is your goal in terms of if you ever want to feed it back successfully. And this was at, what did we say, 9.32. So not bad. I'm not, you know, I've made, so far, I've made a DC-DC converter more efficient, not this one, but others, more efficient than I've been able to see anywhere to buy off the shelf. So I'm happy with that. But aside from, you know, the idea of nodes, as I was talking about before, let's look at two coils in series and things that you can do with them and what happens before. But before I forget all that, I want to put that in a spreadsheet and jot it down. I think we said 9.32. Okay, so it's not like there's a whole lot to show here, but I put two coils, they're close to identical, but call them identical in series, with the start of one, the end of one going to the start of the other one. And because they're not magnetically coupled at all, you know, this could be on its side or whatever, it wouldn't make a difference. And what we see here now is, instead of 160 pulses, it's 304 pulses, because you've got twice the resistance. And instead of the large cap discharging to 9.32, it discharged to 9.34. And why wasn't that 320 pulses? And there isn't anything in a textbook I can find that explains that. I mean, for the textbook, the inductance doubled, and if you measure it, the inductance doubled, and the resistance doubled. So you would think it would be 320 pulses, 9.32, but it improves, and you see that consistently. So that in and of itself is interesting. So here, I've ran that with the coil like that and like that, and that's what we get there. So when they're in series, just far away from each other, it does better than the single coil. And then there's one way that does even better than that, with the same length of wire, and one way that does worse. And so now I want to figure out which is which in terms of, is the better way when the coil is just like that, or is it when it's in a bucking configuration? I'm going to put I can try and look at it, and I'll do that as well, but I'm going to also put a LCR meter on it, and that will tell me also. Okay, so this is good. That's the configuration that was worse, the 9.33 instead of the 9.35, and that's the measured induction. And if I flip it over to the configuration that was 9.35, we get that. So interestingly, there are many more weaker pulses, but it's more efficient. Not way many more, but 5 to, I don't know, however many percent that is, 10-20%. That's interesting. So the bucking configuration works better than that. And what's really interesting is that there's not a good magnetic coupling between these coils with air cores and with how thick they are. Let's wrap this up.